Hello, welcome back to another installment of Boring White Guy talking about mathematics. So, we have finished the integration techniques. We have 2 sections left for chapter 8. These are not new integration techniques, I'm air quoting right now. These are different ways to approach an integral. Let me rephrase that. This is different ways of approaching integrals. The next section is just going to be a whole new type of integral that you've never seen before. Now, I've been trying to keep the videos shorter rather than longer, and I failed with the last video. This section is long, so I started off by writing out the block of text that you'd normally in class, you'd listen to me say 2 words, then I'd write it, then I'd say 2 words, then I'd write those, and it's just a mess. So I went ahead and wrote these out. So the techniques introduced so far actually find the antiderivative. Recall that the antiderivative is just one of them, so let plus c be plus 1 plus 0. That is the antiderivative. It's the basic thing. The integral is the whole collection of them. Small nuance, I don't know why I mentioned it. But what do you do if you can't find the antiderivative, or it can't be expressed as elementary functions? So elementary functions are what you're used to: sine, cosine, polynomial, square roots, exponents, logarithms. Those are all elementary functions. So what if the antiderivative can't be expressed using elementary functions, which basically just means you can't actually sit down and integrate this? So examples of functions that you cannot find the antiderivative of would be the integral, grab the pen, the integral of e to the x squared dx. You can't integrate that. The integral of the square root of 1 plus x to the 4th. It looks like a squared plus x squared, so words are hard today. Use a trigonometric substitution, but the fact that you have to the 4th here really screws that up. And you have the integral of sine of x squared dx. These we can't integrate. There is no elementary function to write down for these integrals. So what we do when this happens, we approximate the integral. So how do we approximate the integral? Going back to Calc 1, you started off with Riemann sums. You approximated the integrals by, finding the area under the curve using rectangles, and then just letting that the number of rectangles get infinitely large. So what we do for that is you replace the function f of x with closely fitting polynomials over portions of the interval. This method is known as numerical integration. So numerical integration is I don't actually want to solve this integral, I just want to get a pretty close approximation to what this definite integral is. So as I mentioned, you've seen this before. You've seen this with Riemann sums. So when I say you replace f of x with a closely fitting polynomials, with Riemann sums, you replaced f of x with a constant function. And that's how you got rectangles. And this resulted in rectangles, as I just said. So we're going to see two new numerical integration techniques that will just do much better than Riemann sums. These have nice long derivations. I will derive the first one. The second one, you can look at the book for a nice derivation, but I don't want this video to be a couple hours long, so I'm skipping it. I'm exaggerating a little bit. It wouldn't be too bad. So the first numerical integration technique that we will cover is the trapezoidal rule. So with the trapezoidal rule, we approximate the area using trapezoids. I know that you did not see that coming. You probably thought circles. So in order to approximate the area using trapezoids, we need to know the area of a trapezoid. So recall that the area of a trapezoid is delta x over 2 times h1 plus h2. Drawing a picture, if this is our trapezoid, this be h1, this be h2, and this be delta x. So as with Riemann sums, as the subintervals increase, so that is as n goes to infinity, aka as delta x goes to 0, the approximate area gets more accurate. All right, so let's check this whole trapezoidal rule out. And let's see what we mean by it gets more accurate. So we have a nice line that I drew too big, so let's make it a little bit shorter. Yep, that looks good. And let's draw a random function. That is a horrible function. That isn't actually a function. There we go. And then let's label, we have x0, which is going to be a. We have x1, x2, x3, and then x4, which is going to be b. Grab a blue-red pen. x0 hits right here, which is y0. x1 hits here. x2 hits here, here, and here. And then for the trapezoidal rule, we just connect the dots. And look, we have a trapezoid. Trapezoid number 1. Connect the dots again in a straight line, and you have trapezoid number 2. And then this looks like a box, but boxes are trapezoids, so that's good. And then connect the dots here. So notice these y0, which is going to be h1 and h2. So here we have h1, h2. These are the height of the function at x1, x0, and x1, which is f of x0 and f of x1. Also, delta x is the distance between two consecutive x terms. Okay, so that's all the notation. And then if we repeat this drawing over here, again, I can't draw functions. But this time, here it looks like we had 4 intervals between a and b. If we had more intervals, then trying to use the same colors, we would have this, we would have this. This would be our first trapezoid, and this would be our next trapezoid, and so on. I don't want to draw them all. So the reason I did this is notice this first trapezoid in the first picture is very off. You have all of this area that it's missing. Whereas if you come over here, since we have more intervals now, we're only missing this much area now. So as we said above, as n gets larger, so as the number of trapezoids gets larger, we get a better approximation of our function. All right, so let's do the derivation. assume that the length of each subinterval is delta x equals b minus a over n. Basically, all we're saying is that we are dividing each subinterval is the same length. Then the sum of the areas of the trapezoids is, you have T for trapezoids, super creative. All right, so we look at the first trapezoid. Well, we have this delta x distance there, so let's go ahead and get that distance. That's delta x over, we said 2. Then we have h1 plus h2. h1 plus h2. Well, h1 is this height, which we said was f of x0. And then h2 is this height, which we said was f of x1. So as f of x0 plus f of x1. Okay, that was the first trapezoid. Let's do the second trapezoid. Second trapezoid, notice we still have what shares a common edge. So we'd have f of x1 again, and then we'd have the next one, f of x2. Okay, that's the area of the second trapezoid, and then we keep doing this for however many we have. So that would be delta x over 2 times, I ran out of space, but that's unimportant. Okay, well, all of these have delta x over 2, so let's pull those out. We then have f of x0 from the first one. We then have f of x1 from the first one. We then have f of x1 from the second one. And then f of x2 from the second one. And the third one, you'd have f of x2 again. And then plus dot, dot, dot. And then you have the last one, which will only appear once as the last edge in the last trapezoid. Okay, well, this is delta x over 2 times f of x0 plus 2 f of x1 plus 2 f of x2 plus dot, dot, dot plus 2 f of xn minus 1 plus just 1 f of xn. Running out of space. Written differently, we have t equals delta x over 2 times f of x0 plus f of xn plus 2 times the summation of f of xi from I equals 1 to n minus 1. We'll go over the summation notation more in the next chapter. So if you don't remember it or don't know it, that's fine. You could just remember the previous equation. I should add a t then. Ooh, t. Okay, so that's the trapezoidal rule. So to approximate the integral, from a to b of f of x dx, use for the trapezoidal rule t equals exactly what I had above. Where, recall that we said delta x equals b minus a over n, and that would mean that x0 is going to be a, so start on the left endpoint, and then x1 moving to the next point would be a plus delta x, and then moving to the next point would be a plus 2 delta x, and then so on. And then xn will also be this right endpoint b. Okay, whole bunch of gibberish. Let's do an example to see this. It's not as bad as it looks. So use the trapezoidal rule. With n equals 4 to approximate the integral from 1 to 2 of x squared dx. And then compare this to the actual result. Integral from 1 to 2. Okay. Solution. Let's find the actual result first. This integral is one of the harder integrals we have. You have to use integration by parts, followed by partial fractions, followed by a trigonometric substitution, followed by looking up something in a table to realize it's just the power rule, as x cubed over 3. I know I'm hysterical. Evaluated from 1 to 2, that's 8/3 minus 1/3, which is 7/3. Okay, but let's use the trapezoidal rule to evaluate this. So delta x, we said, was b minus a over n. In this case, b is 2, a is 1, n is 4. So delta x is 1/4. So our trapezoidal approximation is delta x over 2, which is 1/8, times f of x0, which is 1, the left endpoint, then 2 times f of add 1/4 to 1, so that's 1 plus 1/4, plus 2 f of add 1/4 to that, and that's 1 plus 1/2, plus 2 f of 1 plus add 1/4 to that, 3/4, and then plus 1 f of 2. All right, that is 1/8. F of 1 is 1 squared, which is 1. That is 2 times 5/4 quantity squared, plus 2 times 3/2 quantity squared, plus 2 times 7/4 quantity squared, plus 2 squared, which is 4. So that is 1/8 times, we have 5 from 1 plus 4, plus 2 times 25/4. Nope, that is not how that works. 25/16, plus 2 times 9/4, plus 2 times 49/16. All right, that is 1/8 times. The 2 and the 16 will always cancel out. I failed again. No, I didn't. I'm fine. Always cancel to be 8. 5 is 48. Now you have 25/8. This would be 9/2, which is 36/8. And then you have 49/8. Okay, that is something over 64. 40 plus 25 plus 36 plus 49 is 150. Both of those are divisible by 2, so that would be 75 over 32. All right, it said, so that was our approximation, but it said to compare the result to the actual result. So let's compare. So we have 75 divided by 32 minus the actual result, 7/3. This is 225 minus 224 divided by 96. I'm just trying to subtract this fraction. So get common denominator, which is 1/96. So this approximation with only n equals 4, it overestimated it. Overestimated the area by only 1/96. So that's a pretty good approximation. All right, so that's the trapezoidal rule. The trapezoidal rule means that you approximate the area with trapezoids. We now move to Simpsons rule. So the Simpsons rule approximates the area using donuts. Lol, JK. It doesn't actually use donuts. Using parabolas. So like I said, we're going to skip the derivation, but I want you to see what I mean by this. So I'm going to draw you one picture. I'll do my best to draw this. We have like this. Oh, let's not go below the axis. This. Yeah, let's do that. And then we would have x0, x1, x2, x3, x4, x5, x6, x7, x8. So the Simpsons rule is a little bit different in that you must have an even number of, n must be even so that you can get these. Let me draw and then explain what I'm saying. So between 0 and 2, you're going to draw a parabola where the middle, x1, is the maximum or minimum of that parabola. So x1 is here. So we connect the dots. This looks like it's going to be a maximum, and that's our parabola. You then connect the dots between x2 and 4. Let's try to get this darker so it doesn't look as bad. With x3 being the lowest point. So you'd go like this, and then you go up. As you can see, that trapezoid actually does a good job of approximating. Not trapezoid, parabola. Notice the first parabola missed like all of this. And then same thing with the next one. Here, you can't really have this be the minimum. So you just kind of connect the dots as a parabola. And then same thing with the next one. And again, that can't be the minimum. So you just connect the dots. And I realize that my coloring in has been absolutely horrible. I apologize. But I think this is enough to see what we mean by approximate it using parabolas. And the book has a nicer picture. You should look at the book because they can actually shade things and draw the perfect parabolas. But notice that it gets some curves very nicely. unlike the trapezoidal rule, which will never get a curve nice. Okay, so for Simpsons rule, skipping the derivation, to approximate the integral from a to b of f of x dx, we use s equals delta x over 3 times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus plus 4 f of xn minus 1 plus f of xn. And then let's add right here, n is even. So you're just going to have f of x0 plus f of xn, the endpoints. And then you alternate 4, 2, 4, 2, 4, 2, 4 until you're done. Okay, let's see an example of this. Use Simpsons rule with n equals 4 to approximate the integral from 0 to 2 of 5x to the 4th dx. And then compare this to the actual result. Let's not say actual result, let's say actual value. All right, solution. The integral from 0 to 2 of 5x to the 4th is x to the 5th, evaluated from 0 to 2, is 32. Simpsons rule, we have delta x over 3, delta x, let's write this out. We have delta x equals b minus a over n, which is 2 minus 0 over 4, which is 1/2. So Simpsons rule, S equals delta x over 3, that's 1/6, times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x4. This is 1/6. F of x0, that's going to be f of the first endpoint, which is 0. So that's f of 0. Plus 4 f of add delta x to the previous x value. So that's 1/2. Plus 2 add 1/2 again to get 1. Plus 4 f of adding another 1/2 is 3/2. And then plus f of 2. So this is 1/6 times, 0, plus 4 times 5 times 1/2 to the 4th, which is 1/16, plus 2 times 5, plus 4 times 5 times 3/2 to the 4th, which is 81 over 16, plus 5 times 16. Well, each of these has a 5, so let's factor out a 5. We get 5/6 times 4 over 16 is 1/4, plus 2, plus, we factored the 5 out, that's 81 over 4, plus 16. That is 5/6 times, put everything over 4, so that's 1/4 plus 8/4 plus 81/4 plus 16 times 4, which is, using a calculator, 64 over 4. That's 5/6 times 9154 over 4, which is 385 divided by 12. You can divide this by 2. Each of these are divisible by 2. All right, compare this to the actual result. And you get 385 divided by 12 minus 32. Put them both over 12. That's 385 divided by 12 minus 384 divided by 12, which is 1/12. So Simpson's rule over approximated by 1/12. All right, so we compared both of trapezoidal and Simpson's rule to the exact value, so they were both off. So the next question is, how close can they be? And luckily, we have error estimates for both the trapezoidal rule and Simpson's rule. So the error estimates, we have a block of text. If f double prime of x is continuous and m is an upper bound for the absolute value of f double prime of x on a to b, then the error, I know there's one more r, oops, et in the trapezoidal rule this error satisfies that the error is less than or equal to m times b minus a cubed over 12n squared. Likewise, there's something similar for the Simpsons rule. If the fourth derivative of f is continuous and m is an upper bound, this time for the absolute value of the fourth derivative of f on a to b, then the error E sub s in Simpson's rule satisfies. Absolute value of E sub s is less than or equal to m times b minus a to the fifth divided by 180 n to the fourth. Okay, let's do an example of this and then call it a day. So example, find an upper bound for the error in estimating the integral from 0 to 2 of 5x to the fourth dx, so the last example, using Simpson's rule. With n equals 4. And then second part of this question is what value of n, little n, should we pick so that the error is within 0.001 of the true value? Okay, solution. So to do this, we're using Simpsons rule. So we're going to be using this bound. This bound talks about m being an upper bound for the fourth derivative of f. So we need to find the fourth derivative of f. We also need to verify that it is continuous on the interval a to b. So we have f of x equals 5x to the fourth. Differentiate that, you get 20x cubed. Differentiate that, you get 60x squared. The derivative of that is 120x. So the derivative that we are interested in is just 120. So first off, 120 is continuous on 0 to 2. It's continuous everywhere. And we can bound 120 by 120. I know, very, very hard math there. So we take m to equal 120. Okay, plugging this in, we see that the error term is bounded above by m, which is 120, times b minus a, which is 2 minus 0 to the fifth, divided by 180 times n, which was 4 to the fourth. Well, 120 divided by 180 is 12 divided by 18. Cancel the tens. We then have 2 to the fifth in the numerator. 4 is 2 squared. Raised to the fourth is 2 to the eighth. So that is 12 divided by 18 times 2 cubed. 12 and 18 are both divisible by 6, so that's 2 and 3. And the 2 cancels with the power of 2 in the denominator. So that is 1/12. So notice that the error that we got with Simpsons rule in the last example was the maximum error that we could have gotten. For the second part, we solve the inequality for n. So we have m times b minus a to the fifth over 180 n to the fourth. That is 120 times 2 to the fifth divided by 180 n to the fourth, which is, as before, we can cancel the 120 and the 180 to just be 2/3. So that's 2 to the sixth over 3 n to the fourth. And we want the error to be no bigger than 0.001. Okay, solve this for n. So multiply by n, divide by 0.001. You get n to the fourth is bigger than or equal to 2 to the sixth divided by 3 times 0.001. 0.001 is 1 divided by 1,000. So that is 2 to the sixth times 1,000 divided by 3. I'm getting bored of manipulating these numbers, so take the fourth root. You get n is bigger than or equal to the fourth root of 2 to the sixth times 1,000 divided by 3, which is approximately 12.086. We want n to be bigger than this, so we let n be equal to 13. If you have 13 subintervals, then Simpsons rule will be within 0.01 of the actual result. But recall that Simpsons rule requires that n has to be even, so we actually have to take n to equal 14.